Hello, I'm Henrik Lievonen and I'm presenting you our work on distributed quantum advantage for local problems. This is a joint work with many co-authors. In this presentation, I'm going to start by telling you what I mean by distributed quantum advantage by presenting you the local model of distributed computation. And then I'm going to continue by telling you what I mean by local problems. So after this, you should understand the title of this work. Then I'm going to present you one of the key ingredients in our work, namely games, and how we assemble them into a quantum advantage, that is, the networks of games. Finally, I'm going to summarize our work. But without further ado, let's get started by defining the local model. In the local model, we have a graph that represents a network of computers. Imagine that each node of the graph is a computer and each edge represents a communication link between the nodes. Then our computation proceeds in synchronous rounds. So in one round of computation, each computer first prepares a message based on their local knowledge and then they send it to their neighbors. And based on these messages they receive from their neighbors, they update their local state. And this is one round of computation. And now we continue. Again, in the next round of computation, the computers prepare messages based on their current state, send them to their neighbors, and update their state. And this repeats and repeats until at some point the computers halt and announce their local output. So this is the classical local model of distributed computing. Next, I'm going to present you what I mean by the quantum local model. Again, we have a network of computers that are connected to each other via communication links. But this time these computers are quantum computers and these communication links are quantum communication links. That is, they are able to exchange quantum messages. And now computation proceeds just like in local model. So first each computer does some local computation, this time possibly a quantum computation, and prepares messages for their neighbors. Note that these messages may contain some quantum information that is entangled with the state of the quantum computer. And then these messages are exchanged and the computers update their states, just like in the classical local model. So the main difference between classical and quantum local models is just that in quantum local we have quantum computers. And what this allows the computers to do is to produce some sort of entanglement with their neighbors. So, what do we know about the quantum local model? Well, the seminal result by Gall, Nishimura and Rosmanis from 2019 shows that there exists a computational problem that can be solved in 2 rounds in the quantum local model, but requires a linear number of rounds in the classical model as a function of the size of the graph, that is the number of the nodes in the graph. And this was a great surprise. Because recall that we did not impose any limits on the amount of computation the computers can do in one round, nor did we impose any limits on the bandwidth of the communication links. Especially, even classically, the computers can simulate any quantum circuit locally. But there is a catch. The problem Gall, Nishimura and Rosmanis presented is a global problem. That is, to verify the solution, you need to see the output of the whole graph. In particular, no node can locally verify whether the solution is actually correct. And this is something we usually care when studying the local model. So, in this work, we are improving on this by presenting the first known local problem that shows distributed quantum advantage. In particular, we show that there exists a local problem that can be solved in quantum local model with constant number of rounds, while in the classical model, it requires linear number of rounds as a function of the degree of the nodes. I'm now going to present you more formally what I mean by local problems, and then I'm going to show you how to construct a problem that shows this linear separation between the local and quantum local as a function of the degree of the graph. So, local problems. These are the class of problems that can be verified locally. So, think of a coloring. A coloring is valid if each node can locally check just by looking at their neighbors that their output is valid. For example, a coloring is valid if each node can see that its color is different from all of its neighbors. On the other hand, if the coloring is improper, then there exists at least one node that sees that its color is the same as the color of one of its neighbors, and hence the coloring is improper. Contrast this with some global problems like leader election, where the task is to select exactly one node of the graph. This is a problem that cannot be verified locally. Another local problem is the problem of finding a maximal independent set. Note that here I'm talking about the maximal independent set and not the maximum independent set, because checking whether the independent set is globally the best possible is a global problem. Another problem is maximal matching. Now that I have presented the preliminaries, I'm going to show you the main ingredient in our result, namely games. In this work, by a game, I mean a co-op game that is defined by a relation. For example, in this game, we have an inputs x and y and outputs a and b that must satisfy this relation. Namely, if both of the inputs are 1, then the outputs must disagree with each other, that is, their sum is 1 modulo 2, and in all other cases, the output bits must agree, that is, their sum is 0 modulo 2. So now, how is this game played? Well, we have two players, Alice and Bob, and they, with the knowledge of this game, can discuss a strategy, possibly using some sort of randomness. But once they have fixed their strategy, they are taken away and put into separate rooms. And only at this point they get to know their local inputs x and y. And now they need to decide their outputs based solely on the agreed strategy and their local inputs. And they win the game if the input and output pair comes from this relation. This is the classical model. So, how does this differ in quantum? Well, in quantum, again we have this relation that describes the game, and again we have Alice and Bob agreeing on a strategy. But this time imagine that they are carrying some sort of pocket quantum computers, that when discussing their strategy they can entangle. I'm now going to represent this entanglement by this squiggly line. And now again, once they're happy with their strategy, they're taken to separate rooms. But note that this entanglement remains. And now again, they both get to know their local inputs, and they need to produce their local outputs. And this concept is such an important concept for the purposes of our result that I'm going to present this as these two boxes connected by the squiggly line. So imagine that this is a circuit flowing from left to right, and then there is this magic gate that solves this problem. These gates are so-called PR boxes. And indeed, the game I just presented you is such an important game that it has a name. It is the so-called CHSH game, named after Closer, Horn, Shimony and Holt, who presented this game in 1969 to test the so-called hidden variable theory of quantum mechanics. And why is this such an important game? Well, it can be shown that classically this game cannot be won with probability higher than 75%. While with access to quantum computers, this game can be won with 85% probability. Turns out that this game is such that there exists a so-called non-signaling strategy for winning this game. But for the purposes of this presentation, it's not important to understand non-signaling, so you can just imagine that this is some sort of superquantum world that is exactly like the quantum computation, except that we have access to a magic box that plays this game perfectly. I'm going to return to this later in the presentation and show how we can actually achieve this for real quantum computers and not just for this superquantum world. But for now, imagine that we are living in this superquantum world. So now I'm going to show you how we can assemble these elementary games into the problem of our interest, by showing you how we can combine these into networks of games. So the first idea is that we have Alice and Bob playing this game repeatedly. To classically play this game, you need to communicate, while in the superquantum world we have access to these magic boxes that play this game perfectly with no communication. Okay, so let's see an example. Here Alice and Bob both get zeros as their input, which means that they need to produce agreement. Let's say that they produce both ones. 2 ones means that they need to produce now disagreement, so maybe Alice produces 1 and Bob produces 0. And again now we are in the case where they need to produce agreement, so say they produce zeros. Maybe this is already enough to get a separation between classical and quantum worlds. Not really, because this is also a correct solution. Just output 0 everywhere. Okay, so let's try this again and fix the inputs as 1s. Again, this means that they need to produce a disagreement. So without loss of generality, Alice produces 1 and Bob produces 0. But now we are in the case where the input already contains a 0, which means that the players need to produce agreement. And now, from this point onward, they can always continue outputting 0. And we degenerate in this simpler case. But this gives us an idea. What if, instead of having 2 players, we have multiple players? Say, here Alice and Bob are playing the first game. Simultaneously, Charlie and David are playing a game, Erin and Faith are playing a game, and so on and so on. And now, in each one of these games, the players need to produce some sort of disagreement. Say, without loss of generality, again, Alice produces 1, David produces 1, Erin produces 1. But note that now we have multiple ones in this output still. So what if we add more games? Say, like this. Now, in particular, David and Erin are playing another game, and they both have produced 1s as the outputs from the previous games. So now again, they need to produce disagreement. And now we still have some 1s, again. So maybe we add more edges to this graph. Say, Alice and Erin are now playing another game. And they again need to produce disagreement. And so on, and so on. And now imagine that each row of this circuit is actually one node in our graph, and the edges represent these games the players need to play. And note that this game was constructed such that it is easy to play in the superquantum world, while it is hard to play in local without access to these superquantum computers. In particular, to play this game classically, you need to spend 1 round communicating with your neighbors, while in superquantum you need to communicate just once with each one of your neighbors preparing these games. But after that you can play everything locally. Now, in summary, I have shown you how we can achieve this separation between classical and superquantum. That is, in classical, every player must spend 1 round sequentially playing the game with their neighbor. While in superquantum, the players can just spend 1 round initially setting up these games, and then they can compute the whole result locally. And now, just finally, I'm going to fix that I've been talking about superquantum and not about quantum. The basic idea is that maybe CHSH game was not the correct game. Maybe we could find another game that shows genuine quantum to classical advantage. But alas no, such game does not exist for 2 players. But luckily such game exists for 3 players. The so-called GHZ game, named after Greenberger, Horn and Scheilinger, is such game. It is a game that is hard to play classically, but can be solved with quantum computers with no communication. In short, if all players receive zeros as their inputs, the output must contain an even number of 1s, while if the players receive exactly 2 1s as their input, the output must contain an odd number of 1s. And if the input is anything else, the players can produce anything. And now, by replacing this CHSH game between 2 players by a GHZ game played between 3 players, we achieve our result. That is, we get a local problem that shows genuine quantum advantage. We show this linear in delta lower bound by using the so-called round elimination method. The intuition there is that classically the players must play their games 1 by 1, while in quantum they can spend 1 round of communication initially to set up the games, and then they can locally compute everything. Just as a final note, those well versed into distributed algorithms may have noticed that we show linear in delta separation. That is, the separation is a function of the degree of the nodes. And this is not LCL problem as defined by Naur and Stockmeyer. So, and in a future work, we show how to turn the problem I presented here into a genuine LCL problem that can be solved in log n rounds in quantum, while requiring log n times log n over log n rounds in classical. We do this by embedding virtual high-degree nodes in a low-degree graph and requiring the algorithm to play this game on these virtual nodes. This concludes the presentation.